Let us consider a sample problem of equilibrium with the presence of slide and friction, the equilibrium of a ladder. From experience, we all are familiar with the situation when we have to reach for a thing positioned somewhere high using an accommodation ladder. And when we are setting the ladder, we always check how stable it is going to be against the floor, a wall, or a vertical surface. Then, when we have our ladder set, when we have adjusted a comfortable angle to put it firmly, we start climbing it, and we intuitively feel with our body how high we can climb without falling. Let us solve the problem, which in terms of the engineering mechanics course could be put as follows. At what height a man of 80 kilograms, an average weight of a man, can climb a ladder of 5 meters in length and 15 kilograms in weight, which are characteristics of an aluminum ladder, if the angle it makes with the horizon amounts to 60 degrees. The coefficient of friction are given for the contact of the ladder with the floor in that point and with the wall. Let us designate the point of contact with the floor as the point A and the point of contact with the wall as the point B. The coefficient of friction with the floor is 0.4 and with the wall is 0.3. Now let us consider the diagram of the problem. In the diagram, the ladder is illustrated as a linear segment AB, and the axes are introduced with the origin in the point O. The angle alpha is 60 degrees. Active forces are given as P1 and P2. P1 is the force of the man's weight, and P2 is the force of the ladder's weight. The equilibrium condition for a body with the presence of slide and friction can be articulated as follows. The reaction of a rough surface must be passing inside the friction cone. In our case, we have two rough surfaces, the floor and the wall, and so we have two reaction forces. To build a friction cone and use it for solving our problem with the equilibrium condition, we are to utilize the coefficients of friction, which are directly related to the friction angles. Let us draw a vertical line from the points A and B. And from the vertical in the point A, we lay off the angle phi A, and from the vertical in the point B, we lay off the angle phi B. Those are the friction cone generators. The tangent of the angle phi A is equal to the coefficient of friction with the floor, and the tangent of the angle phi B is equal to the coefficient of friction with the wall. The friction cones look like this. The reactions will be directed into the friction cones. In this case, the ladder with the man climbing it will be in equilibrium. The ladder is under a coplanar force system. The gravitational force P, which is the resultant of the forces of the ladders and the man's weights. The reaction of the rough surface RA and the reaction of the rough surface RB. According to the three-force theorem, which is known to you, if a body is under the action of a coplanar non-parallel system of forces, then the lines of action of these forces intersect in a common point. In other words, the forces P, RA, and R1 intersect in one point. Let us call this point C1. In this drawing, we see the ultimate equilibrium condition, at which the reactions RA and RB are directed along the friction cone generators. Thus, we can formulate the equilibrium condition for the ladder as follows. XC is equal or greater than XC1, where the point C is the point of application of the force P. Let us check this condition geometrically. The point C changes its position as the man is climbing up the ladder. When the man starts climbing up, the point C is here, then here, then here. When the point C is here, In other words, xc is less than xc1, we state that the equilibrium condition is disturbed. Why is it disturbed? And at what point, B or A? Let us draw the force P in this position. Assume that we have the undisturbed equilibrium condition in the point B, and that RB is still directed along the cone generator. Then, according to the three-force theorem, we claim that RA, RB, and P should intersect in one point, in this one. Then RB should be directed like this, and A is coming out of the cone. Therefore, we can show that the equilibrium condition is disturbed in the point A as well. In this drawing, we highlighted red the zone where the equilibrium condition is disturbed, and highlighted green is the zone where the ladder is in equilibrium. To find the height, we are to use the ultimate equilibrium condition, at which xc equals x1. In the problem, we have to determine the ultimate height at which the man can climb. In the drawing, we see the normals, the cone generators, and the ladder. Let us analyze the triangle BC1A. It is defined. All the angles of this triangle we can express through the given angles alpha, phi A, and phi B. Having found the angles of this triangle, we can, by the law of sines, write down the following condition for determining BC1. And we can project BC1 onto the x-axis and thus find the coordinate of the point C1. The coordinate of the point xc we can find from the given condition, which we are to find out later when discussing the center of gravity topic. The coordinate of the point xc, the center of gravity, the resultant of the gravity forces, can be found from the sum of the forces of the ladders and man's weights, and the coordinates of the position of the man and the center of gravity of the ladder. Let us equate the right parts, xc1 and xc, which is the ultimate equilibrium condition for the ladder. Then we have the following expression. To find the height from the equation, let us write x1 and x2. This expression is for finding the coordinates of the man's gravity center in a general form and for finding the coordinates of the ladder's gravity center also in a general form, regardless of the actual position of the man at a given moment. Substituting x1 and x2 into this expression, we can find all the parameters except the height from the condition of the problem. Then, solving this equation, we find the height. For the given conditions, the height is 3.3 meters, which is high enough for a man of 80 kilograms to climb up the 5-meter ladder.